Hello. In this section, we are going to talk about exponential functions. So let's dive right in and start with this official definition of an exponential function. If we let b be a constant real number such that b is greater than 0 and b is not equal to 1, then for any real number x, a function of the form f of x equals b raised to the power of x is called an exponential function of base b. Essentially, an exponential function is any function with a constant base. The base is the number being raised to some power, or to an exponent, right? And the exponent is a variable, so it has a constant base and a variable exponent, right? So examples of exponential functions would be like 2 raised to the power of x, or 3 raised to the power of x minus 1, because in both of those cases the variable term is in the exponent. Now, so far we've looked at functions that involve exponents, but so far all the functions we've looked at, the exponent has been a constant, right? Something like a polynomial function, x squared or x cubed minus 1. The variable is in the base, and the exponent is a constant, right? So these over here are not exponential functions. These are, because the variable term is in the exponent. So what we're going to do first is we're going to look at the graph of, we'll look at a couple of fairly simple exponential functions, and we will take a look at the graph of those functions and some of the characteristics of that. First one we'll look at here is f of x equals 3 raised to the power of x. Okay? And so the easiest way to graph a exponential function is really probably using the plotting points method, where we just choose a few x values, plug those x values in, and solve the function. So I'm going to start with the x value of 0, and if I plug that in here, I'm going to get 3 raised to the power of 0. And one thing about exponents, it's a rule of exponents that anything raised to the power of 0 is always equal to 1. So this is equal to 1. If I do the number 1, I get 3 raised to the power of 1, which is equal to 3. If I do 2, I get 3 squared, which is equal to 9. Okay. And then I could try, so that's, and then let's see, let's try 3. So that gives me 3 cubed, which equals 27. And let's try a few negative x values as well, something like negative 1. That gives me 3 raised to the power of negative 1. Another rule of exponents is that if you have a negative exponent, I can write that as 1 over the same number raised to a positive. So this would be 1 over 3 raised to the power of 1, or just 1/3. Okay? Negative 2, that would be equal to 1 over 3 squared, which equals 1/9. And maybe one more, negative 3, that gives me 1 over 3 cubed, which equals 1/27. Okay? If I plot these points over here on my coordinate system, I have, let's see, 0, comma, when x equals 0, y equals 1. That's going to be right about there. Okay? It's not perfect, but when x equals 1, y equals 3, that's going to be there. When x equals 2, y equals 9, that's going to be there. When x equals 3, y equals 27, that's going to be all the way up here. Okay. When x equals negative 1, y equals 1/3. That's going to be very close down there. negative 2, 1/9, negative 3, 1/27. So all of these will be very close to the x-axis. So if I graph this, basically got something like this. Okay. So what we see is that this function is always increasing, right? And not only that, but as x gets bigger, the graph gets steeper and steeper and steeper. So it's basically increasing at a constant rate. We also observe that the x-axis serves as a horizontal asymptote, where coming this direction, the graph approaches the x-axis, but never quite touches it, right? It gets closer and closer and closer. So it exhibits kind of that asymptotic behavior like we explored with the rational functions in the previous section. So this is a fairly typical graph of an exponential function. Over its entire domain, it's an increasing function. It's defined only for positive values, right? The entire graph sits above the x-axis, and basically all the y values of the graph are only positive. The range is only positive values, and then the x-axis acts as a horizontal asymptote. Let's do another one. This next one is has a negative exponent, 2 raised to the power of negative x. And it's also worth pointing out that, again, just because of some of the fundamental properties of exponents, this could be also written as 1 over 2 raised to the power of positive x. Or an equivalent way of expressing this would be 1/2 raised to the power of x. Okay, so the base is 1/2 and the exponent is x. So again, doing the plotting points method, we'll do x equals 0. So that gives me 1/2 raised to the power of 0, basically, right? 1/2 raised to the power of 0. Anything raised to the power of 0 is equal to 1. So again, that's equal to 1. X equals 1. 1/2 raised to the power of 1 is equal to 1/2. X equals 2. Let's use this form. 1 over 2 squared is equal to 1/4. Okay. X equals 3. 1 over 2 cubed is equal to 1/8. X equals negative 1. If I use this form of the equation, that would be 2 raised to the power of negative 1, right? Which is the same as 2 raised to the power of positive 1, which is just 2. Similarly, negative 2 gives me 2 squared, which equals 4. And negative 3 gives me 2 cubed, which equals 8. If I plot these over here, right, I've got the point 0, 1, which is right there, 1, 1/2, which is about there, 2, 1/4, about there, 3, 1/8, it's getting closer and closer to the x-axis there. Negative 1, 2 is right there. Negative 2, 4 is right there. Oh, my bad, sorry. Let me fix that. Eraser. Oh, shoot. All right, let's try this again. My apologies there. All right, so where were we? Negative 1, 2, negative 2, 4, and then -3, 8. All right, so let's sketch in the graph here. Okay. Okay, so in some ways, this one kind of exhibits the opposite behavior as the previous one, right? With this one, as x increases, the function is decreasing over its entire domain. But as x gets bigger, the graph gets less and less steep, right? So it's decreasing at a slower and slower rate. And again, the horizontal axis serves as a horizontal asymptote, right? The x-axis. It approaches the x-axis but never quite touches it. Okay. If you have an exponential function where the base of the function is a number between 0 and 1, then you'll see the graph look something like this. It'll be decreasing over its entire domain, right? In this case, the base is 1/2, right? Because the function is 1/2 raised to the power of x. Whereas in the previous one up here, this is a very typical graph of an exponential function where the base is a number greater than 1, right? In this case, the base is 3. So if the base is greater than 1, the graph is going to be increasing everywhere. And if the base is between 0 and 1, then it will be decreasing everywhere, like this. Okay. So that's some of the fundamentals of exponential functions. And now I want to spend some time going over a really important application that involves exponentials, and that is basically money that builds interest. And so the idea of interest, this is a consumer math example, right? To start off with, there's really two types of interest. And we'll start by talking about simple interest here. And simple interest, this can apply, there can be really two different applications. Like if you invest money in a bank, like in a savings account or something like that, then it will build interest. You will earn interest on that. Or if you borrow money, then you typically have to pay interest on that loan, right? So interest can work both ways. Simple interest looks like this, or the formula for simple interest is this: I equals P times R times T. Okay, where P is the principal and is the principal. Okay, principal is defined as the amount of money borrowed or invested. Okay, say money borrowed or invested. Okay. Okay, R is the interest rate. Okay, so the way interest is determined, it's using a percentage rate, right? So you would say like a 2% or a 3% interest or something like that, right? And in the formula, the interest rate is given as a decimal. And then T is the time in years. Okay, so like for example, let's say that you borrow $5,000. Okay, maybe you take out a $5,000 loan, and the terms of the loan is that you have to pay that loan back in 3 years, and the interest rate is 3%. Okay, if that's the case, then the amount of interest you would owe, right, would be the principal, 5,000, times the rate. 3% as a decimal is 0.03, times the time, which is 3 years. And you just multiply those together. A simple calculation on your calculator. Let me just do that real quick. 5,000 times 0.03 times 3 equals $450. Okay, so oopsies, 450. Okay, so that means that after 3 years, you would have to pay back not only the $5,000, but also $450 in interest. Or this could work for you as well, right? Like if you invest this money in an account that that earns simple interest, right? Then after 3 years, you would have earned $450 in interest, right? Now, in most accounts, like investment accounts, the type of interest is not simple interest, but it is compound interest. With compound interest, what happens is that the interest is compounded periodically. What that means is that, let's say that maybe if it's compounded, say, monthly, what that means is that every month the simple interest is computed and then it's added back in. And then the next time it's computed, because it's based off of the original principal plus the interest from the first compounding period, then the amount of interest grows each time, right? Because every time you compute the interest, it's based off of a slightly larger principal. So to kind of explore that concept a bit, let me just get some room here. Okay. So let's say that the interest is compounded annually, which means one time per year on an investment of P dollars. Okay. Let's just say P dollars. Okay. Annual interest rate R, okay, for T years. Okay. So we could say this. We could say after 1 year, the amount of money that you would have, we could say total amount of money that you would have in the bank would be equal to the initial principal, okay, plus the interest, right? So the formula for that, the initial principal is P, and then the interest, using the simple interest formula, would be P times R times T. But remember that it's the time period is just 1 year, right? So it would really just be P times R, because T is equal to 1, right? Because we're talking about after 1 year passes. So using the simple interest formula, which is principal times rate times time, this would be the interest after 1 year, right? Because time, or T, would be equal to 1. And then in this, I could factor out a factor of P, and this is equal to 1 plus R, okay? So that's so after 1 year, the total amount of money in the bank is given by this. Now, after 2 years, right? So what happens again after 2 years? So we get to 1 year, and the simple interest is computed on the original principal, right, and then added back in. Well, after 2 years, the simple interest is computed again, but this time the principal that it's computed off of is a larger amount, right? Because it's based off of not just the original principal, but the interest that was computed after the first year, right? So, so this is where it gets a little bit algebraically messy. But after 2 years, we would say that the amount, which I'm just going to call A, okay? Call it A up here, is equal to the amount that was after the first year, right, which was P times 1 plus R. And then we really invoke the simple interest formula again, right? But the principal now is this amount, right? So it's going to be P times 1 plus R. Remember this, the simple interest formula is P times R times T, where P is the amount of money in the account, right? Well, now the amount of money in the account is this. So then I'm going to take that and multiply it by R and then by T. But again, T is equal to 1 because the amount of time that's elapsed is exactly 1 year, right? So this is the amount of money in the account after 1 year passes. This right here is the amount of interest after 2 years, right? So after 1 year, this represents the amount of interest. After 2 years, this represents the amount of interest. And this ends up equaling, what you can do is you can pull out a factor of P times 1 plus R from that. Okay. This is actually basically pulling out a common factor. You get that. And this equals P times 1 plus R squared. Okay. Now you could do a similar analysis and you could find that after 3 years, the formula becomes A equals P times 1 plus R cubed. And, extending that out to an indefinite number of years, you get A equals P times 1 plus R raised to the power of T, right, where T is the number of years that the money is invested, right? So, and this is an exponential formula, right, because it's an exponential function because the exponent is a variable. In this case, the variable T, which represents a quantity of time, okay? But the nice thing about compound interest is that it, over time, it grows at a faster and faster rate, right? That first function we graphed, the 3 raised to the power of x, you saw that behavior is that as x increases, the value of y continually increases, but it increases at a faster and faster rate. That's how compound interest works as well. The longer you leave the money in the account, the faster it will build interest at a faster and faster rate, right? So if you leave it in there long enough, you'll see that this is a much more powerful way of building interest than simple interest, right? Because it continuously compounds. So every time the interest is compounded, it's a little bit more than the previous time, and so on, so forth. Okay. Now, what I'm going to do now is I'm just going to show you a bit of a more generic version of the formula. This formula here assumes basically that it's compounded every year, but that is not necessarily always going to be the case. Sometimes you will have compound interest that compounds daily or monthly or something like that, right? Something other than yearly. So the more generic version of the compound interest formula looks like this. Let's put this up here. Compound interest. Okay, so the formula is A equals P times 1 plus R over N raised to the power of N times T. Okay. So A is the amount of money after time t. Okay, where t is typically expressed in years, right? After t years. P is the principal or the starting amount of money. Okay. R is the interest rate as a decimal. And N is the number of compounding periods per year. Oops. Okay, periods. So if it compounds annually, N would be equal to 1. That would be like what we just looked at, right? But if it compounds monthly, N would be equal to 12. If it compounds daily, N would be equal to 365, right? The number of days in a year, and so on and so forth, okay? So let's kind of look at an example here, okay? Let's suppose that $15,000, okay, is invested. $15,000 is invested. Okay. With 2.5% interest. Okay. So I want to look at two scenarios. The first one is compounded annually. Okay, so using the compound interest formula, I would have P would be 15,000. Okay. Interest rate is 2.5% as a decimal. That is 0.025. Annually means one time per year, so N is equal to 1. Okay. And that is raised to the power. There's one other important piece of information that I left off. The money is left in the account for 7 years. So T equals 7 years. Okay. So raised to the power of N times T, N is equal to 1, T is equal to 7, right? So it looks like that. This is going to equal 15,000 times 1.025 raised to the power of 7. And if you work that out on your calculator, you get $17,830.29. Okay. So what happened is that we started with $15,000. 7 years later, we ended up with $17,830.29. And that was assuming 2.5% interest compounded every year, right, for 7 years. Now let's do the same thing, but this time let's assume it is compounded quarterly. Okay. Oops. Compounded quarterly. Quarterly means 4 times per year, right? So basically in our formula, the value of n would be equal to 4. So what that looks like is A equals 15,000 times 1 plus R over n. N is equal to 4 because it's quarterly, raised to the power of n, which is 4, times t, which is 7, which gives me that. Okay? So the easiest way to work this out would be to just kind of simplify it down part of the way. If I take 0.025 and divide by 4, I get 0.00625. So this basically ends up equaling 15,000 times 1.00625, and then 4 times 7 is 28, so that's raised to the power of 28. And then that you can plug into your calculator, and you're going to get $17,858.96. Okay. So in other words, what you see is compounded annually, that's the amount you end up with. Compounded quarterly, that's the amount you end up with, right? And this number is a little bit bigger than that one. So what you observe is that if you compound more times per year, then the money grows into a larger amount over time. Now, interestingly, there's actually a kind of a ceiling or a limit to how much that growth will actually happen, right? To illustrate that, let's go back to the compound interest formula. Okay. Let's see if I have. Needs a bit more room here. Okay. So let's do this. Okay. Let's see. Draw eraser. I'm just going to make a little bit of room on my board right here. So there's my compound interest formula. Oopsies. I'll fix that in a minute. Okay. To illustrate a point right here. Okay. Go back to my pen. Okay. P times 1 plus R. So, what I want to do is, let's say that I decide to invest just a single dollar. P equals 1. Okay. And I'm going to do that at 100% interest. So interest rate equals 100%. Okay? And as a decimal, 100% as a decimal is just the number 1. Okay? And I'm going to do this for 1 year. Okay? If I plug those numbers into the formula, I get A equals 1 plus 1 over n raised to the power of n. Okay? Right? So basically this is the compound interest formula, but I'm assuming $1 invested in an account that gives 100% interest for 1 year. Right? So the only thing I have not plugged in is a value for n. And so what we want to do is kind of explore what happens when we do different values of n in this formula. And this is something that could be interesting to explore with on a calculator if you have it. But if I do like a little table, say n and a, and try different values, you'll see something kind of interesting. Like if I plug in, say, 100, and you could verify this on a calculator if you want to, but plug 100 into that, I'm going to get about 2.7048. 2.7048. Okay. If I plug in 1,000, I'm going to get 2.7169. If I plug in 10,000, I'm going to get 2.718. And these are all rounded off values, okay? In reality, these keep repeating and repeating and repeating, kind of like the number pi, right? To infinity, we call that an irrational number. It has kind of an infinite number of repeating decimal values, okay? And if you keep going up, what you'll observe is that it tends to approach a very specific number. Okay. If I put in like 100,000, I get about 2.7183. Okay. And if you keep going up, it's going to gradually get bigger, but it's basically approaching a very specific number. In fact, if we say if n gets bigger and bigger and bigger, if we let n go to infinity, we would say that this here, we could say as n goes to infinity, right? It gets bigger and bigger and bigger. This approaches a very specific number, which is a very important number in mathematics, and it's referred to as the number e. And e is used in a lot of applications that involve exponentials. It's an irrational number. It's approximately 2.71828, and so on and so forth. Okay, so it's in this context, in this application, this illustration, it kind of represents the ceiling that compound interest hits, right? Basically, in this case, if you invest just $1, but this is a very important number in mathematics, and for a lot of exponential application functions, the number e is used as a base for that. So in the context of compound interest, we could introduce another version of this, which is compounded continuously. Okay, and if interest is compounded continuously, then the formula is actually A equals P E to the RT. Okay, so we have an exponential equation where the base is E, and then the exponent is the interest rate times the time. So if I apply this to the example I was doing here, again, 15,000 E raised to the power, so 2.5% interest, 0.025 and it's for 7 years, right? And because E is a number that's used so extensively in a lot of mathematical applications, there is on pretty much every scientific calculator, there's a button specifically for evaluating exponentials with a base of E. If you look on your calculator, it'll probably look something like this, just a button that looks like E raised to the power of X. And that would be the button you'd want to use to evaluate something like this. It's usually pretty straightforward to use. If you work this out, you would get $17,868.69. Okay. And so what we observe here is, going back here, let's see, let's just mark this one, right? Compounded annually, we got 17,830 approximately. Compounded quarterly, we got about 17,859, right? Compounded continuously, that's basically saying if you could theoretically compound an infinite number of times, this is what you would make. And what this represents is the absolute maximum that you could possibly make with this account, right? So 2.5% interest, 7 years, your $15,000 would never grow bigger than this amount, regardless of how many times you compound that. It's kind of like represents an asymptotically the top ceiling of how far that could grow, right? Similarly, over here, right, if you invest $1 at 100% interest for 1 year, no matter how many times you compound that, the most it would ever grow to would be about $2.72, right? Which is pretty good. Your dollar grows to $2.72, but this represents the maximum that would ever grow to, no matter how many times you compound it, it will never grow higher than that. So there's a lot of other applications that involve exponential functions. Exponential functions are often used to measure things like population growth. Radioactive elements often decay in an exponential fashion. And there's numerous other examples of where these come in really handy. But compound interest is a very practical one, right? Because we all like to see our money grow. And so it's kind of interesting to explore that, right? And this number E that we kind of derived here, we kind of derived that in the context of compound interest, right? Because that's kind of a nice way to look at it. But that number is used in a lot of other exponential applications as well, right? So that's a very important number. So let's see. I think that is about it for this section. So we'll wrap it up here for today. And thank you for watching this.